Good morning. My name is Vishnuvardhan. I am from Electrical and Electronics Engineering. And today's my analog electronics TikTok topic is signal to noise ratio, dynamic range, and power distraction. Paying attention to their interaction can greatly benefit analog circuit design. So, low power dissipate is paramount in an increasing number of applications. This notable Internet of Things and wireless sensor network in which a battery must have a very long time or in which energy harvesting is used. Battery life is also a key considerable. Traditional applications such as hearing aids and communication devices. All of these applications involve analog signals and require careful micropower circuit design. Such design can be more effective if guided by an understanding of the fundamental limits beyond which nature does not allow us to go. In this article, we revise the relation between power dissipation and signal to noise ratio for analog circuits. We make a crucial distinction between SNR and usable dynamic range and review ways to allow the SNR to vary as needed, thus extending the UDR and resulting in adaptive power dissipation. To be able to provide some depth, we focus on only conventional analog continuous time signal-ended circuits using active elements, resistors, and capacitor references to discussion of other circuits are provided. The circuits are assumed to be in or near thermal equilibrium. All signals are supposed to be held below a maximum value, beyond which unacceptable distortion occurs. We consider first-order effects only, which allow us to make several simplifying assumptions. Supply excess factors and power dissipation. A key to effective micropower design is to be able to use supply voltage and current as effectively as possible. For simplicity, signals will be assumed to be sinusoidal. Later in this article, we will use a transconductor as an example, but the definition applied to other circuits as well. The ideal supply voltage VDD would be just equal to the peak-to-peak value of the signal. Then no voltage could be wasted. The ideal average supply current IDD would be the same operation, which is IP by R, which IP being the peak output current. To quantify how those ideal values, we define two excess factors, one for supply voltage and the other for supply current. We want both excess factor to be close as possible to 1. We can now express the supply power dissipation as follows. P, P by I equal to VE, VE into I DD VPP. We are equal to CM. Noise. We use the well-known noise model shown in figure 2, where T is the absolute temperature and the K is the Boltzmann constant. We assume that we are not interested in extremely high frequencies or extremely low temperature, wherein quantum correction becomes necessary. DF denotes a very small measurements bandwidth and the mean square noise voltage and current with spectacular components in that bandwidth are denoted by E n square D and E 2D respectively. The ratios in the figure to approach the corresponding one-sided power spectacular densities. If DF is allowed to approach zero, En is the so-called excess noise factor because of the extra noise added by the various devices in the transconductors. To find the contribution of a noise source with a known PSD to the output mean so square noise on a circuit, we make use of the transfer function from the noise source to the output. The resulting output mean square noise denoted by N is given. N is often called the noise power, although its units are old. V square not W. Name includes all noises for frequency selective circuit. Noise in both the pass band and the stop band is included. Signals to noise ratio. The so-called signal power S is the mean square value of the output signal voltage US. So these are the figures which will tell us about supply voltage and current access factor defined, and the white noise modules for low and medium frequency works also. This all includes all noises for a frequency selective circuit, noise in both the passband and the stop included. First order resistance capacitance circuit example. We now calculate the mean square noise at the output of the resistive capacitance RC low pass filter in figure with the input signal set to 0. We use with the PSD from figure and HN. This gives the value in figure. Another way to obtain this result is to use the concept of equivalent noise bandwidth, which for the above circuit is 14 by RC when this is multiplied by the PSD of 4 TKR. We again obtain the previously given result. This makes clear why the noise generated by the resistor is independent of the resistance value. Increasing the resistance increases the noise PSD with but decreases the bandwidth in pro- proportion. Yet another approach is to equate the capacitor's average energy and the terminal voltage expected for this system in the thermal equilibrium from statistical physics. This gives again the same result. The capacitor value required in this circuit to achieve a given SNR can be determined from and the equation for n in figure. The result is shown by the third equation in the same figure. The smaller the signal and the larger the required SNR, the larger the capacitance needed to keep noise down. First order GMC circuit example, consider now the first order loss as GM sequence. From the output point of view, this corresponds to a resistor of 1 by Gm driving C, but with noise power multiplied by the excess noise factor. Working as before, we find the noise power given by the second equation in the figure. The equation after that gives the required capacitance for a given SNR. We use that these results are similar to those in figure only multiplied by the excess noise factor En. We can determine the power distribution from supply as follows. The peak capacitor current IP is given by using in this C from the third equation, and the result we obtain the power expression as given by the last equation in the same figure, where we have assumed that the signal frequency is equal to the cutoff frequency filter FC. Note that the first three factors in the right hand side depends on specifications and design performance. The rest of the factors though are due to the laws of nature. To double the SMR, we need to use twice the capacitance and thus twice the transconductance to leave the corner frequency intact. This halving of impedance levels requires twice the current for the same swing, thus doubling the power. Each 3 dB improvement in SNR requires doubling the power dissipation and capacitor area. In this respect, life is easier with digital circuits. So these are the figure 3 and 4, which tells us the first order RC low pass filter and a first order GMC low pass filter. According to the previous equation, the minimum required power can be expected to score linear with SNR. Compare this to digital, where the power is Logarithmic with SNR, analog to digital conversion, digital to analog conversion do not allow taking function advantages of this because they are governed by analog limitations. So, conclusion, we have received ways to estimate the Popper dispersion expected of simple circuits from fundamental consideration. For a given circuit, a lower bound can be determined for overall dissipation, which is proportional to frequency and SNR. Various partial limitations contribute to exceeding this lower bound. This has been quantified by defining three axis factors: one for supply voltage, one for supply current, and one for noise. ISNR circuits can be prohibited in terms of power dissipation, especially if they are highly selective. However, in most of the cases, ISNR is used just to provide a larger UDR. In these cases, as we have shown, we can design for a large UDR while the SNR is only as large as the specification dictate gain by a smack noise. Power adaptation in the case of large desired signal and small interface. Smack, noise. Alternative power adaptation in the case of a small desired signal and small interface. Smack, noise, before adaptation. After adaptation, power adaptation in baseband filter in the case of a small desired signal and small interface. Thank you.